Hello guys, welcome to the Technology 4 in 1 series, and I myself Talab Kalevendan, a software engineer for the past 15 years. And since this is my first video on this series, I will just explain about why this series and what this series is all about. So as the name suggests, there will be four four common things that I would be discussing. The four common things can be an algorithm, or it can be a data structure, or it can be a technology, or it can be a concept, but they would be having something in common between them. And why this approach is because this had helped me in the past. Out of the four, one or two would be already known to you guys as a software engineer, and the other two things would be slightly different from that, and it will be a uh, additional knowledge on top of the existing one. So what I mean to say is that, like, it would be a differential knowledge of the first one. So so usually some of the tougher concepts will not go and stick in your mind, uh, because like you would approach the problem as a fresh one. But if you are having that problem as a differential one of the first one, it will stick in your mind forever. So that's the whole idea. And since this is my first video, I wanted to take the one of the important topic in data structures and algorithms. And the reason why I'm taking this is because it will set as a precursor for the following discussion that I'm going to make in the future. Okay, the topic is time complexity. So the topic is time complexity uh, in the algorithmic world. Let's say the algo world. So as you all know that, like, time complexity is a bigger concept. I don't want to get into the 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 real computations, the real mathematics behind it, because the whole idea of this discussion is that to make the things simplified and make you to understand in a different way than the usual ways that is available in the internet. Okay, the four time complexities that I'm going to discuss are O of n, which is otherwise called linear time. The second one is log n. Whenever you say log, there is a base 2 hiding here, so it's log n, which is called logarithmic time. And the third one that I'm going to discuss is the combination of these two, which is order of n star log n. And the fourth one, what I'm going to discuss, is order of n square, which otherwise called a quadratic time. Okay, now people would be thinking, like, why only these four? I mean, like, why not other things? Or is there any other algorithms available, time complexities available? Yes, there are many things are available, like O of n cube is there, O of n cube is there, uh, O of 2 power n is there, O of m to the power of n is there. There are many things are over there. Sometimes uh, uh, there are n to the power of n is also there. So many algorithms are available. The reason why I'm comfortably ignoring all those things is because these are the worst algorithms in terms of the time complexity. Okay, so you can ignore I mean, there are some algorithms where you cannot achieve anything better than n cube. uh, those are the exceptions. Otherwise, you strive hard for those four time complexities that we have discussed in the previous page. Like, you always work for you will always work for order of n or log of n, or you try for at least n star log n, or at least to the best extent n square. So even n square for some of the algorithms are considered to be the worst time complexities. So it depends on what algorithm that you are working on and what you are trying to achieve. Okay, so and also there is one more time complexity called order of one, which is called a constant time. This also I'm comfortably ignoring. The reason is because there is nothing to teach over here. Like, you are getting, you are seeking for something and you are getting that one at the first attempt itself. For example, an ordered map, or a hash map in Java, where where you would just where the values would be stored as a key value, and the key is your hash value of the hash of that particular value. So when you search for that, you'll directly get into that location and return that value. So it would be it would return the value at just at one shot, and hence there is nothing interesting about it to discuss on that. So I just ignore that. But otherwise, order of one is one of the is the best algorithm that you can achieve. And coming to that next thing, what is big O notation? Let me go from the basics, right? So what is big O? Big O is nothing but a measure of algorithmic speed. There are better definitions and better formal definitions available in the internet, but what I'm just simplifying it in my own words. This is as simple as how a kilometer is for a distance. It is just you just have to so big O is nothing but uh, big O of something x is nothing but a speed of your algorithm. So this decides how fast or how good your algorithm is, and that is the reason why you strive hard for the best one of that one. Okay, so just to give a quicker recap, so what we have done is the four algorithms that we are going to compare are order of n, log of n, order of n star log n, order of n square. Now, how do you find? Okay, let me give order of n. The first one, linear time. Now, how do you find an algorithm whether it is running in order of n or not? Uh, there are many mathematical way to find it, but I have seen some of the fresh students, or even some experienced student, finding difficulty in terms of finding an uh, the big O notation of a particular function or something. So it is actually simple. Otherwise, if you map it in your mind in a simpler way, it is actually very simple. For example, let's say you there is a function which is finding if a number is present, or a number it is present or not in a sorted array. Note this point. Okay, so which means that you already have a array which is in sorted order. So it will be like 2, 4, 6, 8, 10, 12, 14, something like that. Okay, so you are going to search a number from this one. All right, so how do you search this number? uh, so in a simple brute force way, your algorithm would be something like so there is a find number function, which would be a bool, find number, which would be taking a vector of int of array. And what you would be having is, you would be having a for loop which is ranging from 1 to n of that array, where n is the size of the array. And you would find, like, if okay, there will be one more parameter called um, there'll be one more parameter called uh, int your number, my num. So what you would say, if array of I is equal to my number, you would return true, and after searching that one, and if you never find it, you will return false. All right. So sorry for my scribbling, so I just wanted to make it a little faster. So this is how you do that, right? So this is the simplest brute force way. So what you are trying here is, like, let's say if the number that you are searching is 8, let's say that is the number that you are searching. So what you would do is, you'll just compare it with the first number, then the second number, then the third number, and you compare it with 8, and you find that number and you'll return it here. So you have typically taken 4 steps to reach it, but instead of 8, if this number is 14, what you would do is, you'll just go till this last value and you find it and you return it. So typically you'll go to the 7 steps to reach that value. uh, uh, what is that 7? Which is nothing but the n. So you typically take n steps to reach that particular value to find the address. Or otherwise, let's, if the number is 27, which is the number which is never present in there, you have to exhaust the entire array to make sure that, like, the number is not present. So still it will take order of n. So at so what you are trying to say here is, like, at worst case, you have to exhaust the entire array and see whether the number is present or not. Otherwise, the time complexity of this algorithm is order of n. To make it very simple, or to have it in your mind very simple, if at all a for loop which is ranging from 1 to the size of the data structure, then the size, the for loop determines the order of your algorithm. So here, if you look into a for loop, and if you found there is a for loop which is running from 1 to n, then that is your order of the algorithm. As simple as that. You don't have to do any other thing. I mean, like, whether you're exiting somewhere in the middle, yeah, of course you would be existing somewhere in the middle, but, like, obviously that is for a special case, but otherwise you would be doing that one for the entire 1 to n. So that is the order of your time complexity of your algorithm. For example, the next question arises, like, what if I have a for loop, like 1 to n, and I have one more for loop here. I mean, this is stupid to write like this, but, like, let's say your function demands like this. Your function is demanding like this. So, and so there are two for loops that are running. So so is that like n square? No, it is actually 2 times of n, right? So your order of, so the time complexity of this one would be order of 2n. It is always, you can always comfortably ignore the constants that is proceeding with that. All right. And let's say, what if this is order of 1 to m, and what if this is order of 1 to n? So is this like order of n into m? No, it is still not. because see, you are running this one separately and you are running this one separately, and they are not intertwined between them. So it is not order of, so it is actually, if n is greater than m, then then for this one the order, it will be order of n. If m is greater than n, then this is actually order of m. That's all. Right. So you don't have to worry on this particular things. So 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 that's how you have to compute the order of any algorithm. Okay, coming to the next one, which is log n, logarithmic time. So here, as I already told you, there is a base 2 is hiding. There is a big mathematics behind it, but let's not enter into it. Whenever you say an algorithm is running for log of n, what you need to do is that you have to try to raise this n to the power of 2, and this x is your time taken. For example, let's say if the total number of elements in the array is 16, and how you can write this one is like 2 to the power of 4. So 4 is your time complexity. Let's say if this is a very big number like 1204, can be written as 2 to the power of 10. The time complexity is just 10. So what that means is within 10 iterations I would find the number that is being present in there or not. So if you are converting the previous algorithm, whatever that I was discussing, like to find a number to a algorithm which is running in the logarithmic time, then that is a big win. I mean, like since I mean like uh, even for a 4 or 5 digit number, the logarithmic time would be considerably very less. So that is the reason why all, for some of the algorithms, you always try to find the logarithmic time complexity of of that the alternative logarithmic time complexity way of finding the algorithm. Right. Okay, so for this one, for the previous problem, how, the best algorithm is obviously binary search. So what you would be doing is that you have array called 2 4 6 8 10 12 14. So what you would do, you just take the middle of it, and you try to see whether my value is there or not, whether my value is that one or not. If that value is, if my value, let's say my value is 14, if my value is greater than this value, then there is no need for me to search anything from here, because obviously since it is sorted, these values, which means that these values will never fit into my category. So what I have to do is I will comfortably ignore this, and I will go to this half, and I will try to divide this half into two, and then compare with the middle element of that one. So I'll just compare with 12, and I'll see, like, I mean, 12 is like is my number. No, my number is even bigger than that. So I will comfortably ignore the entire path. Then I will go here and I will see. So within 3 iterations that I have found a value instead of going for 7 iterations. All right. So so now you would be thinking like, what if this number is not the in which cannot be raised to the power of 2. So find the next possible, let's say your total count of um, uh, elements in the array is 28, right? So you just move that one to 32 and raise that one to 2 to the power, and this is the maximum time that is going to take. Fine. So that way you can simplify and understand this particular problem. Okay, so now you have a fair understanding about the logarithmic time. So the logarithmic time is the best time that you can achieve for this kind of problems. Now, why I'm the third algorithm that I'm going to talk is about install log. Why, I mean, like, usually people won't discuss this particular time complexity because it's nothing but a combination of n and a log n, whatever that you have discussed in the previous uh, s- uh, just few minutes before. So why I am interested in this one? The reason why I was interested in this one, because sorting, this particular technique, sorting, falls under this category. What I mean to say here is, like, the best of the best sorts that you can achieve is, I mean, there are some tweaked sorts that you can achieve better than this, but like they are very complex to implement. But the commonly written sorts like quick sort and heap sort or a merge sort would take a time complexity of n log n. So that is the reason why this is a very important algorithm that you need to keep it in your mind. So what that means is, there is a for loop which would be running for 1 to n, and inside the for loop there is something which is running to 1 to log n. That's how you have to visualize this problem. So um, what you are doing in terms of achieving this for loop is going to define your algorithm. I mean, whether it's a quick sort or a heap sort or it's a merge sort. All right. So let's not get into it, but that's how you are going to do to achieve this one. And also um, there will be problems in your function. Let's say you have a function and you would say sort um, v dot begin and v dot end, and after that you would be doing for loop for 1 to n, and you complete it. And when people ask you what is the time complexity, since you have written only for loop from 1 to n, then you would be saying that, like, okay, my time complexity is linear time. No, you have to consider what are all the inbuilt functions that you are using inside your function. All right, so the inbuilt function that you are using inside this function is this sort function. This sort function is internally using some sort, either it may be a quick sort or a merge sort. Usually it will be a quick sort. So that means you are running your function in n log n plus order of n. So I think, like, since this is the biggest one, the time complexity of your function is O of n log n. That is very important that you need to keep it in your mind. Okay, now the next one is your quadratic time. So quadratic time is very straightforward. That again you need to um, quadratic time is very sorry. Uh, okay, this one is better, I believe. Yeah. Oh no, this one is better. Yeah, so your quadratic time is nothing but order of n square. All right. So um, what that means is, now by now you'd have understood what is that. So it is like 1 to n, and you would be doing 1 to n. So there is a loop within a loop, then this particular problem would be running for order of n square. Let's say you don't have um, let's say you don't have sorry what I can do is I'll just let's say, okay, I'll just make it a little complex. Let's say you have one more for loop here, 1 to n, and you have it here. So what is this? Is this one is order of n cube? No, this is still order of n square, because these two for loops are running separately. Let's say if you are running for 1 to n and for 1 to n and for 1 to n and like this, then this is going to be your order of n cube. Otherwise, this is order of n square. So that's all for today. Hope you have enjoyed your session. Thanks. I'll meet you in the next session. Thank you.